Hello, welcome to the Masterclass on 64-bit. Houdini, since Houdini 12, I believe, we rewrote the geometry library and supported 64-bit attributes. Unfortunately, the support for 64-bit attributes does not extend to everything in the pipeline, so usually this was a rather moot point because they'd stripped down to 32 bits when you did any processing with them. With Houdini 18, we've added some key tools to be 64-bit and actually have a solver which is able to run completely in 64-bit mode. So it's time to start looking at how you work with 64-bit data. So I'm going to start off with a rubber toy, whose name, by the way, is Flip with an exclamation mark. And if we look at the rubber toy, we can see it draws perfectly fine. Now let's transform them off into the distance. So when I transform him, if I transform him a simple amount of distance, like 1,000 points, and let's make that actually 1,000 rather than 100, we'll see that if we home in, it looks like the normal flip and everything is the same. But if you've worked with floating point, especially 32-bit floating point, you know that there's a magic number that shows up. The magic number is 24 million. At 24 million, floating point stops being able to tell different integers apart. So you can't even do, if you do x and x plus 1, you might get the same result as you had to begin with. So let's try this out. We're going to move Flip way off in the distance. So 10 million units over. And I'm using the underscore here as a separator because that way I don't have to try and carefully count the number of zeros I type in. I can see at a glance I've just moved 10 million units. If I go over here and hit space H, we can see the viewport is not the least bit happy with this. Our flip has been turned into like 6 horrible quads as they got quantized down to the closest possible points. Let's try and undo this. So I'm going to do another transform SOP, and I'll transform back the opposite. So there's an optional transform called invert transform. This makes it pretty simple to undo the previous operation. Go back to the origin, and we can see this has not preserved the quality of our flip. It has indeed quantized the points because it wasn't able to represent them all in 32 bits. By the time you add the 10 million prefix, the last digits where all the interesting data of flip were get truncated, and we end up with this ugly result. If we go to geometry spreadsheet, we can see again that our positions here are highly quantized. They're either going to be 0 or -1. They're not allowed to have any interesting values in between, which really destroys our data. So what we can do to work around this, and it actually has existed since Houdini 12, is we can change our position attribute to 64-bit. If it's a 64-bit number, adding 10 million leaves a lot of precision still left, so it's still able to fully support these very large transforms. You have to transform over more like 24 million times 4 billion distance to get the same result. So that's a huge distance. So let's do an attribute cast. The attribute cast SOP is what you can use to convert the precision of attributes. So in this case, I can put it down and ask to convert the precision of the P attribute, and I will change it to 64-bit. Now, you notice immediately that the result of the transform and transform was the correct result. We actually successfully transformed the flip way off in the distance and back again. So I just want to go through that again to make it clear. Start with the attribute cast. It looks the same, 32-bit and 64-bit. But after I transform it, we can see here the GL viewport is working in 32-bit, so it's not happy with this result. But all the data was preserved, so if I transform it back, we have the correct results. There's a few places you can go to find out if something is 64-bit or not. The first one is the middle mouse button menu. So I middle mouse on a node, or I use the info option on the ring menu. So if I bring up the information menu, we can see here that P is 3 floats. FLT stands for float. It's a type position that controls how it gets transformed. And there's a little tiny micro text here saying 64 to let us know that it's a 64-bit attribute. Normals right now are 3 floats. They're transformed as normals, and there's no suffix, which means that it is 32-bit, because that's the default. We didn't want to spam the interface with a bunch of 32s that don't mean anything. We also see this in the geometry spreadsheet. So if I go to the geometry spreadsheet, I can see here there's a little subscript 64s for P and none for the N. Now you can also do more crazy things here. For example, we do support going down to something like 16-bit float, in which case we'll see _16, but of course that's even less precision. So usually we only care about the 64-bit. That can be useful if you're trying to reduce the amount of data stored on disk, and you have something like color or something which does not require full precision. Now, we've got a 64-bit attribute, and as a result of that, the transform SOP knows how to transform 64-bit attributes. So this is then preserved in this move to 10 million and back again. Let's try this again, but this time we're going to use a couple attribute wrangles to move it back and forth. So I start off with a similar idea. P plus equals. And again, Vex also supports the underscore for specifying the amount. And so I can avoid having to worry about separators. Cut and paste that node, change it to minus equals to undo it. And you note that this didn't work. Oh, sorry, hidden space there. I still had interest in the window. So this didn't work. We ended up with the same garbled results we had before. This is because the Vex engine runs in 32-bit. And this was the main holdup, I think, for us to go into a 64-bit pipeline before, was almost everything in Houdini goes through Vex. So if going through Vex caused you to change to 32-bit, there wasn't much point worrying about making everything 64-bit. But with Houdini 18, some people who are more observant will notice some of this actually started showing up in earlier versions of Houdini, but we're now ready to actually bring it to the forefront. Under the bindings tab, there's a Vex precisions option. And I can change this from to 64-bit. And again, on the original node, change to 64-bit. And now it actually did the Vex computation in both cases in 64-bit, so we had no loss of precision when we processed it. And the interesting thing to talk about here is that the Vex code here didn't change at all. Let's just change this a little bit and make it more explicit. So I can say float delta equals 10, 1 to 3, 1 to 3. And P vector pause equals at P, pause plus equals delta, and at P equals pause. So this is just trying to make this explicitly typed, just to make it clear what is actually happening in Vex. So there is no double type or float type in Vex. There's only the float type. Likewise, there isn't a double vector and a float vector. There's just a vector. And actually the same for integers. So in 64-bit mode, int will be 64 bits long. And in 32-bit mode, it'll be 32 bits long. This means the Vex code doesn't require any changes whatsoever to go between the two different modes. Let's now, in between these two attribute wrangles, let's add a point jitter. So let's first configure this a little bit better. So I'm going to put the point jitter at the end and say, yeah, that's ugly jitter. Let's just do a little small amount of jitter like this. And so that works at the end. But now let's try put it in middle of this chain. And if we look at this, we've just destroyed our data. So again, what happened here is the point jitter SOP inside has an attribute VOP. And the problem is, of course, it ran in 32-bit mode. And so it destroyed all the P attribute that it touched. And we realized this would become a serious problem because there's a lot of HDAs that have been created, ones we've created and ones you've created, which don't know about 64-bit versus 32-bit. So they'll all be in 32-bit mode by default. And then you're going to end up with cases like this where you keep losing your 64-bit geometry. So we added the idea of preferred precision. So if we look carefully at the attribute wrangle, the actual precision to begin with was not 32-bit, but auto. Likewise, I can change this one, binaries to auto, and disable the point jitter, and we see we're back to running in 32-bit mode. So the auto mode uses the preferred precision of the geometry, and this is stored and can be changed by the attribute cast. So there's an option here for global precision to set the preferred precision. So default is unchanged, and the default, namely what it is if we haven't set anything, is naturally 32-bit for backwards compatibility. But if I set the precision to 64-bit, we get a badge show up on the nodes showing what the preferred precision is. Currently, this is this cute little bug badge. That might change at some point before or after release, so don't fall in love with it too much. See, this is 64-bit geometry badge, so it can be turned on or off here, depending on if you want it or not. This is the hint that the geometry going down this pipe is going to operate in a preferred 64-bit manner. We can also see this as a detail intrinsic. So if I go to the geometry spreadsheet and go to details, intrinsics, there should be precision, and we can see it's now 64, and the original one was 32. That's a way you can tell what the preferred precision is programmatically if you need to. But the result of that is quite simple. Now these attribute wrangles are going to run in 64-bit mode. So again, I can switch the attribute cast back to 32-bit, It doesn't work. 64-bit it does. And excitingly, the point jitter also will respect this. So even though this point jitter stop has not been unlocked, has not got any precisions promoted, it will just transparently start working in 64-bit because we've set it up that way. The other thing to look at is what happens when we create new attributes. So in here, I can add, for example, a CD attribute. And so I've added a random CD attribute. And the type that it gets added then is 64-bit. So any new attributes created by an attribute VOP or attribute wrangle will be done in the current preferred precision. The same happens if I use the things like add point attribute or set point attribute to create an attribute. This goes on. Another way to create attributes is, of course, attribute create. And so attribute create has an option for precision. It's always had a precision option, and it previously defaulted to 32-bit. And we've changed the default to auto. So any new attribute creates you create will follow the current preferred precision. So if I go here and check the type of attribute, move that over, we can see attribute is type float 64. But if I change the preferred precision back to 32-bit, the attribute create here will create one of type float. So you note here we had explicitly set P to 64, but the float stays as 32, so it's created in that preferred precision here. Likewise, if we set to 64, we'd get a forced 64-bit attribute. This does result in a problem because while the VEX nodes that are buried inside your HDAs will properly promote automatically to 64-bit, the attribute creates inside your HDAs will not. So for example, the color SOP in the release build, the gold 287 build has a problem where it will not respect the preferred precision flag. The first daily build, it'll start to respect it, and that is because this attribute create was hard-coded to 32 previously. So you may have to update your HDAs to change their precisions to auto from 32-bit for compatibility. In addition to the attribute VOP, of course, there is the volume VOP. This also has a similar VEX precision option, default into auto. And the interesting thing with volumes, though, is the volumes themselves, the field data is always in 32-bit. So this affects the attribute creation. So if you're making points or looking at points, and so that actually brings up an important point. I've been showing here that you need 64-bit if your geometry moves very far from the origin. Another time you need 64-bit is if you have a very large amount of geometry. And if you have over 2 billion points, you will need 64-bit in order to index those points. Now, the other big thing used for a lot of our solvers, in addition to VOPs and volume VOPs, is, of course, OpenCL. And OpenCL has its own set of problems. So if we look at the OpenCL SOP, and I encourage you not to look at the OpenCL SOP, is that it has a precision attribute at the front, but each parameter it creates, there's now an option for which precision to bind it at. And so when I create a node parameter called foo, let's say, if I take the default here and generate the kernel, we'll see it creates one called int. And so that's going to be a 32-bit size. If I go here and change my precision to 16-bit, then when I generate the kernel, we'll see it'll try and bind to a short. And if I change it to 64-bit and generate the kernel, you'll see it generates a long. And in the OpenCL standard, short, int, and long are defined as 16, 32, and 64 bits, which is kind of nicer than C++, where long, you have absolutely no idea what size it is, and it can vary from platform to platform and operating system to operating system. The other choice here, though, is what's called node, and this is sort of to allow that auto behavior. So the auto behavior then will use this precision over here. So if I set it to node currently and generate the kernel, we see it creates something called accent. And it will define accent as the size that it's selected. So in this case, as an integer. And if I add another binding, so let's add a attribute binding, attribute bar, and type node, and float, generate this kernel, we can see we brought in fp real star bar. So we're binding the attribute as either a double or a float. So the fp real and the accent will be type deft to the appropriate type for the kernel. This allows you to write one kernel that can work with both 32 and 64-bit types. And within that kernel, if you need a 32-bit value, use int. If you need a 64-bit value, use lon. And if you want to use whatever is the best bound, you use the accent. So this will, both Vex and OpenCL, I should point out, will do the proper conversion for your attributes. So if you have a 32-bit attribute and you bind it as 64-bit OpenCL, it'll be converted to 64-bit, sent to OpenCL, and then converted back to 32-bit when it needs to be written back. The same thing happens with attribute VOPs. I mean, that was clear previously because if you had a 64-bit position, it would be downgraded to 32-bit transparently. It wouldn't be an error. But likewise, if you have a 32-bit position, it'll be upgraded to 64-bit. The computation will be done and will be saved out as a result. Now let's look at a case where this actually all comes together in one coherent system. So I'm going to start off with a grid. Let's make it 50 by 50. And do a Vellum configure cloth. And select a few points to be pinned. Nice to create a little setup like this. And now do Vellum solver. Restore our play bar, and we can hit play, and we can say, okay, yes, this is good. We have a little piece of cloth falling down. All is excellent. But what happens if this cloth is far from the origin? Now, the Vellum solver uses second-order position-based dynamics, and unfortunately, those are extremely sensitive to numerical error compared to just using velocities and accelerations. So we don't have to move very far from the origin for bad things to happen. So I can actually go to this grid and just transform it. I don't have to transform it 10 million, where obviously it'll completely break down, but a mere translation of 10,000 will actually be enough to cause problems. Let's see if I can type 10,000 properly. And again, I will invert the transformer and bring it back to the origin just so we don't have to change our viewport over to the distance. There we go. So if I run this, this is actually running 10,000 units from the origin. We'll see that we actually get some ugly behavior in the cloth solve. You see all this crazy liveliness where it's actually seeming to come alive and not properly converge. So our solution to that is to simply run in 64-bit. So we continued this idea that we set up earlier, preferred precision, to try and avoid the need for the Vellum solver or Vellum cloth to know anything about 64-bit. There's no settings here to change to 64-bit. Instead, if you want to solve with 64-bit, you give it 64-bit geometry, and it will automatically decide to do so. So before I do the, it's kind of important you do this before you do the configure, because what we need to do is get both the main path here and the constraints path both to be in 64-bit mode. So because those will be created from the main input, I just need to make sure that attribute cast is first, tell it to run in 64-bit mode. And I'll also want to, of course, actually make my position 64-bit. So I'll just change all attributes here to be the preferred precision, which will make them 64 bits. Now I've got 64-bit position. And when we hit play, we can see we get less choppy results. There is a speed penalty to this, and it definitely depends on your type of video card. So a lot of the consumer cards have very poor double performance, and so they get rather crippled in performance. The CPU has rather minor costs, but in comparison. So there we go. I hope this shows some of what has been done for 64-bit support. We still have continued work to do to get all the other nodes to become 64-bit. It'll probably take a very long time. So if you end up going through a node that doesn't support it, you'll notice your data does get quantized. But at least there's ability to make 64-bit paths now, which should open up a lot of possibilities for not having to reframe the origin all the time. So thank you very much for your time, and enjoy.